A $400 wind turbine can genuinely beat solar panels for your home, but only in a narrow set of conditions most people never actually check before buying one. This video walks through the real physics, the real math, and the real installed costs, so you can make that call for your own specific property with confidence instead of guessing. Most people assume rooftop solar automatically wins every single home energy comparison, and in most cases they are right, but small wind can outperform solar in exactly the right location. That single exception is worth understanding properly, because dismissing wind entirely means missing out on a genuinely useful backup option for the specific homeowners whose property actually fits the profile this video is about to describe in detail. The words right site do almost all the work in that sentence, because if the site is wrong, the turbine becomes nothing more than a spinning lesson in bad assumptions. Keep that phrase in mind throughout the rest of this video, because it is the single filter every other number and every other claim needs to pass through before it means anything for your own home. By the end of this video, you will know exactly when a cheap wind turbine actually beats solar, when it does not, and how to tell the difference before you spend a single dollar. You will understand the real physics behind why wind is so much more site-dependent than solar, the actual math behind realistic energy output, and the honest, total cost of ownership that most product listings conveniently leave out of the picture entirely. Let's start with what a $400 turbine actually is, because the honest answer is not what most people picture in their heads. Understanding this one category correctly will save you from comparing the wrong kind of machine against solar entirely, which is exactly the mistake most clickbait comparisons make from their very first sentence. When a video title mentions a roughly $400 turbine, it is almost never talking about a utility-scale machine or a professionally installed tall tower system. It is talking about a specific category of low-cost small wind kits commonly marketed to off-grid users, hobbyists, cabin owners, boat owners, and rural homeowners looking for backup power. These machines are often advertised in the 400 to 500 watt class, sometimes higher, and they are usually sold bundled together with a charge controller included. Here is the catch that most buyers miss completely. The advertised wattage is a rated maximum, reached only at one specific wind speed, often far higher than the average wind most homes actually experience throughout the year. Manufacturers are not technically lying when they print that number on the box. They are simply reporting the absolute peak output the turbine can theoretically reach under laboratory or ideal field conditions that rarely match the actual weather patterns most residential properties experience on an average Tuesday afternoon. This is exactly the same marketing trick used across dozens of other consumer electronics categories, where a peak number looks impressive in an advertisement but tells you almost nothing about typical, everyday, real-world performance once the product actually arrives at your home. Understanding why that matters requires understanding one basic fact of physics that shapes everything else in this entire comparison. Wind power is brutally sensitive to wind speed, because the available energy in moving wind scales roughly with the cube of that wind's velocity. That means a modest drop in wind speed causes a genuinely huge drop in the power actually available to the turbine, far larger than most people intuitively expect. Picture wind speed dropping by just half, from 10 miles per hour down to 5 miles per hour, and the available power in that wind does not simply drop by half in response. It drops to roughly 1/8 of its original value because of that same cubic relationship. This single mathematical relationship is the single most important concept in this entire video because it explains why a location that feels reasonably breezy to a person standing outside can still be a genuinely poor location for a small wind turbine trying to generate consistent, usable power. A turbine advertised at 400 watts in strong wind may produce only a small fraction of that number under ordinary, everyday wind conditions. This single fact explains why the spec sheet on the box can look genuinely exciting, while the real battery bank sitting in your garage barely notices the machine is even running. It is also exactly why height matters so much for any small wind installation, because wind near rooftops and tree lines is usually turbulent and significantly slower than wind measured higher above open ground. Now let's actually do the math, because numbers make this comparison far clearer than vague marketing language ever could. The most useful way to explain this is through average energy production, rather than the peak power number printed proudly on the box. If a 400-watt turbine somehow averaged a 10% capacity factor over time, it would deliver about 40 watts on average, or roughly 0.96 kilowatt hours per day. Multiply that out across a full month, and you land at approximately 29 kilowatt hours produced, which is a genuinely modest amount of usable energy for an entire month of spinning blades. At a 20% capacity factor, that same turbine would produce roughly 1.92 kilowatt hours per day, or about 58 kilowatt hours across a full month. At a 30% capacity factor, monthly output would reach approximately 87.6 kilowatt hours, which starts to look genuinely useful for a small off-grid system. Here's the honest catch behind all three of those numbers. 20 to 30% is an ambitious capacity factor for many bargain small wind setups, especially in turbulent, suburban locations with nearby obstructions. Some field studies and market observations suggest small wind performance varies wildly in the real world, with many installations underperforming owner expectations by a genuinely wide margin once they are actually mounted and running. This gap between advertised potential and real-world results is precisely why so many small wind reviews online read like disappointed diaries, owners describing a turbine that spins constantly but barely seems to move the needle on their actual electricity bill or their battery bank's charge level. The lesson here is not that small wind never works. It is that the 10 to 30% capacity factor range genuinely depends on a specific, favorable site. And assuming a favorable site without actually measuring your own local wind conditions first is where most disappointed buyers go wrong from the very beginning. Now compare all of that directly against solar, using the exact same rated wattage for a fair, apples-to-apples comparison. A 400-watt solar array or panel rating is also technically a laboratory maximum, but solar output is usually far easier to estimate than wind, because sunlight patterns are simply more predictable than micro-scale residential wind patterns. In a location receiving around 4 peak sun hours per day, a 400-watt solar setup can generate roughly 1.6 kilowatt hours per day before system losses, or about 48 kilowatt hours across a full month. In sunnier locations, receiving closer to 5 peak sun hours per day, that output rises toward about 60 kilowatt hours per month before losses are even factored in. Solar also tends to come with lower maintenance requirements overall. No moving blades to wear down, less noise pollution for you and your neighbors, fewer vibration issues over time, and generally simpler expectations for the average homeowner to manage. A solar panel sitting quietly on a rooftop essentially just needs occasional cleaning to remove dust and debris, while a wind turbine has actual moving mechanical parts constantly exposed to weather, vibration, and mechanical stress that gradually wears components down over months and years of continuous operation. This maintenance gap matters enormously for anyone who does not consider themselves particularly mechanically inclined, because a failing solar panel simply produces less power gradually over time, while a failing wind turbine component can fail suddenly and sometimes dramatically, especially during exactly the high wind conditions when the turbine is working hardest. So can a $400 wind turbine actually beat solar in a real-world comparison? The honest answer is yes, but only when the comparison is framed correctly and fairly. It can beat an equivalently priced small solar setup specifically in a windy, open location with poor sun exposure, especially if your energy demand happens to occur at night, during storms, or during winter months when solar production naturally falls off. Wind also complements solar far better than it ever truly replaces it, which is an important distinction most video titles conveniently leave out of the conversation entirely. In many off-grid systems, the genuinely smartest answer is a hybrid approach, solar handling daily predictability during sunlight hours, and wind providing crucial backup support at night and during bad weather. Off-grid cabin owners who have actually lived with both technologies side by side, rather than simply reading about them online, consistently describe this hybrid combination as far more resilient than either technology could ever be on its own, precisely because the weaknesses of one system tend to line up with the strengths of the other across most weather conditions throughout a typical year. A cloudy, windy winter storm that leaves solar panels producing almost nothing can simultaneously be one of the best days of the entire year for a properly sited wind turbine, and that natural trade-off is exactly what makes the combined system so much more reliable than betting everything on a single power source. The right headline tension here is not wind destroys solar. It is that cheap wind becomes surprisingly competitive specifically when geography and timing stop favoring solar the way they usually do for most homeowners. Now let's talk about the real site requirements, because this is exactly where most viewers will badly underestimate the actual problem they are facing. This is arguably the single most important section of this entire video, because every dollar figure and every capacity factor number discussed earlier depends entirely on getting this one variable right. Small wind works best where average wind speeds are genuinely good, and where the turbine can physically be mounted well above any nearby obstructions like trees, roofs, or neighboring buildings. A common rule of thumb in small wind guidance suggests the rotor should sit substantially higher than anything within a meaningful radius, often around 30 feet higher than any obstacles within roughly 300 feet of the installation. Exact recommendations vary depending on the specific site and the specific turbine model, but the general point behind this rule is completely non-negotiable. Turbulent roof edge wind is simply bad wind for power generation. This single fact is exactly why so many roof-mounted consumer turbines end up disappointing their owners after installation. They may spin constantly, but spinning is not the same thing as generating meaningful energy efficiently or quietly. Picture standing on your own roof and watching a small turbine blade spin briskly in what feels like a decent breeze. The visual impression is genuinely convincing, and it is easy to assume that visible motion translates directly into meaningful electricity production happening behind the scenes. The reality is that turbulent, chaotic airflow near a rooftop causes the blades to constantly change direction and speed in small, inefficient increments, meaning a lot of that visible spinning motion never actually converts into the smooth, sustained rotation that efficient power generation genuinely requires from a well-designed turbine. This is a completely different situation from a turbine mounted properly on a tall, freestanding tower positioned well away from any nearby buildings, trees, or other obstructions that would otherwise disrupt the smooth, laminar airflow the turbine actually needs to perform anywhere close to its rated specifications. There is also a major difference between large-scale utility wind and the small backyard wind category we are discussing throughout this entire video. Utility wind farms often achieve genuinely strong capacity factors because they use tall towers, giant swept rotor areas, carefully chosen sites, and full-time professional maintenance crews keeping everything running smoothly. People hear that modern industrial wind power is impressively efficient, and they naturally assume a backyard machine somehow inherits the exact same economics, but it simply does not work that way in practice. The small backyard turbine faces a lower hub height, far more turbulence, a much smaller rotor swept area, a higher relative maintenance burden per watt produced, and far less forgiving tolerance for installation errors made by an inexperienced homeowner. A utility-scale turbine might sit on a tower reaching well over 200 feet into the air, capturing smooth, powerful, consistent wind flow far above ground-level obstructions, while a typical backyard small wind kit might only reach 30 or 40 feet if the homeowner is genuinely committed to a proper installation, or far less if budget or local restrictions force a more modest, compromised mounting height. That difference in height alone can mean the utility turbine is capturing wind speeds nearly double what the backyard turbine experiences at its much lower elevation. And given the cubic relationship between wind speed and available power discussed earlier in this video, doubling wind speed can multiply available power by a factor of roughly 8, which explains an enormous portion of the efficiency gap between these two very different scales of wind technology. Cheap turbines also raise legitimate quality control concerns that a fair comparison video simply cannot ignore or gloss over. Some low-cost units carry optimistic power ratings on the packaging, limited long-term durability once exposed to real weather, weak documentation for installation and maintenance, poor corrosion resistance in humid or coastal climates, and controllers that are simply not as robust as serious off-grid users would genuinely prefer. Bearings, blades, slip rings, the tail assembly, overspeed protection, and braking behavior all matter enormously here, and any weakness in even one of these components can undermine the entire system's reliability over time. A turbine that only survives light, occasional use, or becomes noisy and unreliable after a relatively short period of regular operation can lose any theoretical economic edge over solar surprisingly quickly. Consider a turbine that costs $400 up front, but requires a replacement bearing after 18 months of use, or develops a persistent rattling noise that eventually forces the owner to simply disconnect it out of sheer frustration. That same turbine has effectively become a far more expensive investment once you account for the wasted purchase price alongside every hour spent troubleshooting a system that never delivered its promised output in the first place. Reading genuine, detailed customer reviews, rather than relying purely on manufacturer marketing claims, is one of the most important steps any potential buyer can take before committing money to this specific category of product, since the gap between advertised durability and real-world durability tends to be larger here than in almost any other home energy product category currently on the market. Hidden costs often include the mounting pole or tower structure itself, guy wires for stability, concrete for the foundation, diversion load equipment to protect the battery bank, additional wiring, batteries if the system is running off-grid, and ongoing maintenance time that rarely gets factored into the initial sticker price. A $400 turbine is almost never actually a $400 installed energy solution once every one of these additional costs gets added up honestly. A realistic total budget for a properly mounted, properly wired small wind system, including a tower tall enough to actually clear surrounding obstructions, often lands somewhere between $1,500 and $3,000 once every hidden cost gets factored into the final total, depending heavily on the specific property and how much existing infrastructure the homeowner already has in place. That is a dramatically different number from the headline $400 price tag that originally caught most viewers' attention in the first place, and it is exactly the kind of detail that separates an honest comparison video from a purely clickbait, one designed only to generate views. The strongest comparison point in favor of wind involves seasonal and temporal mismatch, something solar simply cannot address on its own no matter how well it is installed. This is the argument that genuinely tips the scale toward wind for the right property, and it deserves careful attention rather than a quick dismissal. Solar panels only generate meaningful power when the sun is actually available, and output can collapse dramatically during heavy cloud cover, winter months, or high latitude periods with very limited daylight hours. Wind, by contrast, can genuinely produce power at night and during storms, exactly when solar output has already dropped to nearly nothing. In some regions, the windiest periods of the year actually align with the least sunny months, which makes wind disproportionately valuable specifically as a system balancing resource rather than a primary power source on its own. Many temperate climates around the world naturally experience their strongest, most consistent winds during autumn and winter storm systems, precisely the same months when daylight hours shrink and cloud cover increases, dragging solar output down to its lowest levels of the entire year. This natural complementary pattern is not universal across every single climate zone on Earth, and any homeowner genuinely considering this hybrid approach should look at their own specific regional wind and sun data before assuming this same helpful pattern applies automatically to their particular property. Local weather station data, often freely available through National Meteorological Services or dedicated wind mapping tools, can reveal whether a specific property actually experiences this favorable complementary pattern, or whether both wind and sun simply drop off together during the exact same difficult winter months, which would significantly weaken the case for adding wind to an existing solar setup. If this video wanted one dramatic but completely factual closing line about this exact comparison, it would be that solar gives you reliable daytime harvest, while wind can bail you out precisely when the sky stops cooperating with your energy needs. There are also hard physics-based reasons not to oversell wind power potential, even in a video specifically designed to defend it against unfair dismissal. The BETS limit tells us that no wind turbine of any size or design can ever capture more than 59.3% of the kinetic energy present in moving air, no matter how advanced the engineering behind it becomes. This is not a limitation of cheap manufacturing or poor design choices. It is a fundamental law of physics that applies equally to a $400 backyard kit and to the largest, most sophisticated utility-scale turbine ever engineered anywhere in the world. If a turbine somehow tried to extract all of the wind's kinetic energy in a single pass, the air behind the rotor would have to come to a complete stop, which would actually block incoming wind from ever reaching the blades in the first place, creating a physical contradiction that makes 100% efficiency permanently impossible for any conceivable turbine design. Understanding this fixed ceiling helps explain why even well-engineered turbines never claim anywhere close to full efficiency in their marketing materials, and why any consumer product claiming otherwise should immediately raise a serious red flag for anyone considering a purchase. Real machines, especially cheap consumer models, capture meaningfully less than that theoretical maximum once you factor in real-world inefficiencies and imperfect blade design. Electrical and mechanical losses reduce usable output even further beyond the BETS limit itself, chipping away at whatever power the blades initially managed to capture from the wind passing through them. Cut in speed matters enormously too, because below a certain minimum wind speed, the rotor may not generate any genuinely useful power at all, no matter how long it continues spinning in a light breeze. Rated power, the exciting number printed on the box, may only occur in wind conditions that many residential sites experience quite infrequently throughout an average year. Survival speed and furling behavior matter significantly during storms, because a turbine that cannot protect itself in genuinely high winds may fail at the exact moment its theoretical output would otherwise be at its absolute strongest. Furling refers to a turbine's ability to automatically turn itself partially away from extremely strong wind, reducing the surface area exposed to the airflow, and protecting the blades and generator from mechanical damage during a genuine storm event. Cheaper turbines sometimes lack a reliable furling mechanism entirely, or include one that is poorly calibrated for the specific wind speeds a given property actually experiences, meaning the exact windstorm that should theoretically produce the turbine's best output of the entire year can instead become the event that permanently damages or destroys the machine. This creates a frustrating irony at the heart of budget wind power, the very conditions that make a site attractive for wind energy in the first place. Strong, consistent, sometimes stormy wind are also the conditions most likely to destroy a poorly engineered budget turbine if it lacks adequate storm protection built into its design. For real home practicality, a clear audience split genuinely helps clarify who should actually consider this option seriously. Wind is far more plausible for rural properties, ridgelines, open plains, coastal areas, working farms, and off-grid cabins, where tower installation is genuinely realistic and nearby neighbors are not sitting just a few meters away from the spinning blades. Solar usually wins decisively for suburban rooftops, dense urban homes, low-maintenance households, and anyone who simply wants predictable, reliable performance with far fewer moving mechanical parts to worry about over time. Noise, vibration, local permitting requirements, visual impact on the neighborhood, bird safety concerns, and maintenance access all become much more serious practical problems the moment a turbine gets mounted close to living space in a residential area. Many suburban and urban municipalities have specific zoning restrictions or homeowner association rules that limit or entirely prohibit residential wind turbine installations, regardless of how favorable the local wind resource might theoretically be for power generation, which makes checking local regulations an essential first step long before comparing any actual equipment or pricing options. A rural property owner facing far fewer of these regulatory restrictions, combined with genuinely open exposure to consistent wind and greater physical distance from neighbors, represents almost the ideal candidate profile for this entire technology category, while a suburban homeowner surrounded by trees, other houses, and strict local ordinances represents almost the opposite situation entirely. The economic verdict here needs to stay genuinely careful and honest, rather than chasing a viral, oversimplified headline. If a video promises that a $400 turbine will usually outperform solar for the average homeowner in an average location, that specific claim is simply weak and misleading. That kind of oversimplified promise ignores the cubic relationship between wind speed and power, ignores realistic capacity factors, and ignores the hidden installation costs covered earlier in this video, all in favor of a punchy headline designed purely to generate clicks rather than to genuinely inform a viewer's actual purchasing decision. If instead, a video argues that a cheap wind turbine can outperform a similarly priced solar setup specifically under very windy conditions, especially within a hybrid off-grid system, that claim becomes genuinely much stronger and far more defensible. The best factual position to land on is that small wind is a legitimate niche solution, but it is not a useless one, contrary to what some overly dismissive critics might suggest online. Its fans are not always wrong about its potential. They are often just talking about a specific site class that most ordinary homeowners simply do not actually have access to. A rural farmer with wide open exposure to consistent prairie wind and an experienced neighbor who owns a tall grain silo tower has an entirely different practical experience with small wind than a suburban homeowner surrounded by two-story houses and a dense tree line blocking airflow from every direction. Both of these homeowners might watch the exact same enthusiastic online review, yet only one of them is actually positioned to replicate those same promising results on their own specific property, which is exactly the kind of context that gets lost whenever a flashy headline promises universal results without acknowledging just how site-dependent this particular technology genuinely is. The best possible ending for this entire topic is almost paradoxical once you sit with it for a moment. Most viral home energy content promises a single, universal winner, solar always wins, or wind is secretly better than everyone realizes, when the honest, less exciting truth is that the right answer depends entirely on the specific property being discussed. The cheap turbine becomes most genuinely impressive the moment you stop thinking like a typical suburban consumer and start thinking instead like a site-specific energy planner evaluating your exact property. For the wrong home, small wind remains clearly inferior to solar in terms of output certainty, ongoing maintenance, and overall day-to-day simplicity for the average owner. For the right home, especially one with strong nighttime wind and comparatively weak winter sun exposure, it can genuinely punch above its modest price tag and do something solar simply cannot do entirely on its own. The real battle here was never actually wind versus solar in the abstract, the way most clickbait titles frame it for views. Is bad sitting versus good sitting, marketing wattage versus genuinely realistic average output, and peak output fantasy versus honest, grounded, average output reality. Every single number covered throughout this entire video, the capacity factor math, the BETS limit, the hidden installation costs, all point back toward this exact same underlying truth that a home energy decision made from a spec sheet alone will almost always disappoint, while a decision made from real, measured, site-specific data has a genuine chance of actually paying off over time. There is one specific home energy setup that solves this entire dilemma without forcing you to pick a single winner between wind and solar at all. That hybrid setup, and exactly how much it actually costs to build for a typical off-grid cabin, is what the next video walks through in complete, practical detail. Go watch that video next, because once you see the real numbers side by side, you will understand exactly why so many experienced off-grid homeowners refuse to choose only one power source. The gap between a spec sheet promise and a real-world electricity bill is exactly where most home energy disappointment comes from, and the next video shows precisely how to close that gap before you spend a single dollar on equipment.